So our next speaker will be Sean Cavanaugh from Harvard University, and take it away.
Great. Okay, so I'm just going to jump straight in. So today, for time, I'm mostly going to focus on this recent project looking at identifying a specific type of defect configuration. But in general, I have a handful of ongoing projects in this area trying to use machine learning potentials to look at defect behavior. So do please come speak to me afterwards if you're in any way interested in this area. I do also have another longer talk today later on. So if you're interested in this general space, you can come check that out too. Okay. So what do I mean when I say defects? Well, defects are atomic level impurities in the arrangement of atoms in solids that are present in essentially every bulk material. So this can be something like a vacancy, where we have an atom missing from its typical lattice site. We can also have substitutions, where we have a chemically dissimilar atom at the site of another species, or we can have interstitials, so we have an additional atom located in the interstitial voids within our host framework. So the presence of these defects in materials, whether unintentionally or intentionally, in which case we'd call them dopants, can drastically affect the overall properties of materials, and this is important across a wide variety of applications. And in fact, it's often said that defects in some form or another govern the performant properties of most functional materials. So typically to model defects, we create a supercell with the defect, relax the structure, and then take the energy difference between our relaxed defect supercell and a pristine or bulk defect-free supercell, taking this energy difference along with some small corrections to give us the final formation energies. A key issue that we often have with this approach, however, is that often the initial state of this gradient relaxation can lie closer to a local minimum on our potential energy surface, which yields this higher energy metastable defect arrangement, which may not reflect the true defect behavior. So to avoid this issue, we often apply structure searching strategies to scan our defect energy surface and identify the ground and metastable states. So in particular, we've developed this shake and break approach which has been found to be both accurate and efficient in navigating the defect configurational landscape and identifying these energy lowering reconstructions. So in particular, today I want to talk about this recent independent project I pursued in this space, looking at the behavior of a unique type of defect or defect structure, which is known as a split vacancy. So these can be thought of as a complex between an interstitial and two neighboring vacancies, as shown in the figure here, where essentially if we think about going from the simple point vacancy or typical vacancy, where we have our missing atom from the site here, we have a neighboring atom displaces from its lattice site into this interstitial position near the vacancy, and then forming this interstitial plus two vacancies complex. So these defects have been shown to be important in a handful of cases, most notably in gallium oxide, which is used in power electronics, where you get this drastic energy lowering when you find the split vacancy, as well as in some works on candidate transparent conducting oxides that I've been involved in, where they limit hole dopability. The issue, however, is that they're actually extremely difficult to identify. So the only reason they were found in this case in gallium oxide was that when Joel Varley, in this work from 2011, went to calculate the migration pathway of the gallium vacancy, found that the expected transition state of the migration pathway was in fact much lower energy and was actually the true ground state of this defect, which had a lot of serious implications for its behavior. So while shake and break has miraculously revealed these split vacancies in one or two specific cases, in general it does not perform particularly well at identifying this specific type of defect reconstruction. And that's because it is somewhat unique, and it is what we would call a non-local reconstruction. So unlike typical defect reconstructions or rearrangements that would usually involve some movement of the neighboring atoms around the defect site, or first nearest neighbor shell or the second nearest neighbors, this actually involves the movement of a defect much further away from the defect site, moving closer to the defect. And so the local structure searching strategy employed by shake and break and some other recently developed approaches will be unable to identify these reconstructions in the majority of cases. So I wanted to dig deeper into this type of defect. There have been only a handful of observed cases of this behavior, but again, there's this question of whether this is due to an inherent rarity in nature, or actually just due to the fact that we haven't really had the tools or the methods capable of identifying them previously. So what I find is that the underlying energetics of these states are actually quite simple, involving mostly just electrostatics and some strain effects. So if I enumerate all possible split vacancy configurations, just using some simple geometric analysis within the handful of materials which have shown this, this type of defect thus far, and then compute their electrostatic energies using a simple electrostatic model, or essentially the Madelung potential, what I find is that those which give lower energies than the simple point vacancy when we relax them with DFT, which are indicated by the X's here, are in general some of the lowest energy configurations according to our electrostatic energy model. So showing that it is really just mostly electrostatics governing this behavior. In general, the lowest energy configurations are not exactly the lowest energy ones predicted by the electrostatic model, but just very close to being so. And so this is a good but not perfect screening metric. So using a test set of a few hundred stable metal oxide materials and employing this geometric followed by electrostatic screening, I find that you get these split vacancy geometries for around 10% of all cation vacancies within this test set, which is quite a high prevalence rate for a previously unknown defect configuration. So here I find that the electrostatic model does quite a good job at pre-screening for this behavior, but again is not perfect in that it still gives a couple thousand candidates which need to be relaxed with DFT to actually evaluate whether or not they will form these split vacancy arrangements. So taking advantage of the fact that while they come with this enormous configuration space to search through, the underlying energetics of these defects, as I said, is quite simple. It's just electrostatics with some strain effects and having minimal covalent bonding contributions or charge localization. So this suggests that machine learning interatomic potentials, which are trained on large data sets of DFT calculations, could be sufficient to actually predict their formation. So taking my DFT calculated test set from these oxide materials and evaluating the performance with a few popular machine learned interatomic potentials, I find that a standard model can successfully predict the energetic preference for split versus simple vacancies in around 90% of cases. So accounting for the fact that the prevalence rate of our split vacancies is of course lower than simple vacancies, so around 10% of cases, this corresponds to a true positive hit rate of over 50%, which is there, a false positive rate of just 1% and a true negative rate of 99%. If I try and take a more exhaustive approach where I want to favor identifying as much split vacancy geometries as possible, and so consider all machine learning predicted split vacancies with energies within 0.35 electron volts of the split vacancy or of the simple vacancy state, this then increases to a true positive hit rate of over 80%. And so considering this machine learning model as a screening approach, this results in a 2 orders of magnitude reduction in the number of DFT calculations we need to do to identify these split vacancies, which is already out of a 2 orders of magnitude reduced subset due to our electrostatic pre-screening here, compared to all possible candidate split vacancies. So just one other point to mention here is that I've trialed both the MACE and the NIQUIP interatomic potentials for this task, which thus far have achieved similar accuracies, but with the NIQUIP model being around twice as fast due to some recent infrastructural developments, which my colleague Chun Wei will be discussing in his talk on Wednesday. So I wanted to go bigger and see if I could demonstrate the presence of these defect states across an even wider range of material space, leveraging this drastic machine learning acceleration. So this machine learning acceleration allows me to scan all known crystalline inorganic solids given in the ICSD, as well as all predicted metastable materials on the Materials Project database. So using the geometric and electrostatic screening procedure implemented in the doped package, this gives us around 200 million candidate split vacancies, which is then reduced to around 1 million candidate low energy split vacancies when considering the simple electrostatic screening. If I then evaluate these with the machine learning foundation models I discussed in the previous slide, this gives tens of thousands of identified lower energy split vacancies as compared to the around 10 previously known cases of this defect. Looking at the correlating properties with the prevalence of these energy lowering reconstructions, the clearest trend I find is with the point group symmetry of the cation site, where higher symmetry sites, as quantified by the point group order or number of symmetry operations, corresponds to greater prevalence of low energy split vacancies. So this is likely related to the fact that the higher symmetry sites come with a greater electrostatic loss and more unfavorable dangling bonds. And so in those cases, split vacancy states are more likely to reduce the electrostatic energy. So some key takeaways here are that there are in fact many, many more split vacancies than were previously realized in inorganic crystalline solids, and that they are a much more common motif for vacancies in solids than previously realized. I think this is a nice early demonstration of some of the potential utility of foundation machine learning potentials in this space of defects, but they should be taken with some important caveats, namely that the only reason they work so well in this case is that our underlying energetics are so simple, just electrostatics and strain, but coming with this enormous configurational search space. For many of the other types of defect reconstructions we often see, I know from testing these models that they in fact perform terribly for most of those cases. Okay, and so with that, I will finish by saying that these models can be incredibly useful when used intelligently, but perform terribly when not. So thank you for your attention.
We have time for a quick question while the speaker is setting up the next speaker to come up.
Yeah, really nice talk. So my question is, maybe on this standpoint, so how do you try to figure out the possible split vacancy points that you're testing?
Great. So yeah, the question was, how do I figure out what are the candidate split vacancies? So yeah, so I did kind of mostly gloss over that. Essentially what I do is using this defect package doped that I've developed, look at all possible vacancy sites in the material, as well as all possible interstitial sites, and then look at the product of these two, so all possible these two vacancies plus interstitial, which is essentially what a split vacancy is, with some constraints that I say that the vacancy and interstitial must be within 5 angstroms of each other, that the interstitial shouldn't be any closer than 1 angstrom to one of the host atoms, and then this is essentially how we enumerate the space of candidate split vacancies. Okay.
Thank you.